Okay, so we've gallivanted around the cannonball.
Yes.
Let's go back to what distinguishes quantum mechanics from classical mechanics.
Yes. Okay. So we said the classical mechanics is the thing that I can think of, made of small pieces, and everything works, and I can study these pieces as small as I want. I have absolutely no problem. And then you say, okay, but now I have an electron. I have an electron. I want to study the electron. I can't take a red marker and say, oh, I'll put this dot on the electron, right? You can't say, how do we measure electrons? I don't know. You have electrons, you scatter some photons off of it. These are the type of experiment that you do. You can't just say, oh, I'm going to scatter the electron, but only of this portion, right? No, either you interact with the whole of the electron or none of the electron.
And is that actually what defines a particle?
I would think yes. Yes. And again, it's... how can I say? It depends on the circumstance. So if I'm talking about a proton, right, at a certain scale, at a certain level of energy, the photon comes in, interacts with the whole thing, and is not going to tell me anything about the substructure. So in those particular settings, I would say, aha, my proton is irreducible. Meaning, not that there is no substructure, is that I can't probe it. So anything that I can describe is only at the level of the whole object. And there is no a physical process that depends on the substructure. If I am in those conditions, I can say my object is irreducible. But then I say, okay, now I take photons and I probe the same object at higher energy. Now I can probe the substructure. And now the thing is not a single particle, it's not a single quantum system, because I can probe the inside. So I can't just use a single wave function.
So the proton is not a single particle at that point.
Exactly.
But the substructures, they are single particles?
Right now it's a mess. It's a little bit of a mess to tell you what the proton is. My wife actually studies the structure of the proton, especially on the spin side, and there is a whole problem of the spin crisis there. It's very complicated, but you can't describe the proton as a single particle. And so now you have an electron, right? An electron, we haven't found any scale, any energy level at which we can see an internal structure. So we can always assume, at least so far, that the electron is a single irreducible thing, because there is nothing that we can study. But maybe in 100 years, somebody very clever will find a way.
Strings underneath.
Whatever. And then it's not going to be a single.
No. Now, in the example of strings, you don't say the electron is made of multiple strings. You would say that one string in some vibrational mode is the electron.
Mm-hmm.
So would that be a substructure? Would that technically be a substructure? No, well, okay, forget about strings. What I mean is, let's say there's something else that a mini electron inside the electron. In order for you to be reducible, do you have to have more than one subpart? Or can you just have a smaller part?
Well, the whole needs to be the sum of the parts. So as long as you have one part, you're going to have another part that you have to put together. But then you're also assuming that in classical mechanics, you're assuming that you can give a state to each part independently from the other. Because you're saying the sum of the parts is studying the parts independently is the same as studying the whole thing. And this is not true in quantum mechanics, right? So if I have two particles that are entangled, that system is irreducible. Even if there are two particles, that system is irreducible. I can't describe the system as, oh, there are two parts and I can interact one part and study the motion of one part. No, you can't do it. So quantum mechanics has a way to compose things and still be irreducible, right? And so if you have something inside, what's going to happen is that you're going to have multiple parts, and then you're going to have a quantum. So here, the assumption, I still have to prove, again, as I said before, we get to quantum mechanics in sort of a physicsy, hodgy-podgy way. I'd like to do it very precisely because I want to be assured that there is only one way to create this quantized object. And right now, I don't know that there is only one way.
And this is why you don't believe reductionism, even though it's associated with physics, is ultimately should be associated with physics. Maybe it shouldn't. Same with mechanisms.
No, it's fine to have reduction, but you have to assume that your physics description at some point will stop. Because either we'll assume I have a fundamental structure, or in the case of quantum mechanics, I can't observe below this threshold. That this is the level at which I can manipulate the system.
Yeah. What I mean is ultimately fundamental physics should be about what's at the fundament. So what is irreducible? And if it's what's irreducible, then it can't be reduced and it can't be described with reductionism.
Right. Yes. Yeah. So the point is that either I have a system that is reducible, which I would think it's just quantum mechanics, right? Or I do not, but then what you're doing is just putting the level of the irreducible system below it.
Right. What are some of those 12?
Well, the four physical one we already discussed. Deterministic and reversibility in terms of counting states, conservation of information entropy, conservation of thermodynamic entropy, which means reversibility in the thermodynamic level, and conservation of uncertainty for peaked distribution. Those are the physical one. For the mathematical ones, there are the set of equations that you have. You have the fact that the volumes are conserved, the fact that densities are conserved, the fact that the flow is incompressible. If you look at a phase space, how the flows goes around, you take an area, this flow is incompressible, and then that the symplectic structure is preserved, that the Poisson brackets are preserved. And then if you take the flow, rotate it 90 degrees in phase space, the curl of that flow is 0. I think they should be all of them. But anyway, so that's what I like doing, because the more hats you have, the more intuition you get, and you can tie things a lot together. Because now I know that, the curl of the flow is somehow related to the conservation of information entropy, right? Why is that? And then you look, that's what's happening. And
take us through some more of those insights that you've had where you've examined something. It could be physics related, but it could also be math or computer science related, or even even you're a musician as well, even music related, where you thought you understood something, you realized you didn't, and then you observed it from multiple angles and gained.
Yeah. So the most beautiful thing, it's when you don't even think that there is an explanation and then you find it, because that's totally surprising. So when we do physics, we are taught that the math is the stuff for mathematicians, right? And we discrete, continuous, whatever. It's a topology. What is this? And again, because I wanted to really understand these things, I said, okay, I need to understand what topology is. And what I found was that there is this link between, as I said, verifiable statements to open sets in a topology. For somebody who knows not know what a topology is essentially a collection of sets for which you can do a finite intersection and an arbitrary union. So you have two sets, you can do the finite intersection, 3 sets, you can do the finite intersection, but you can't do it. Now, there is this translation between set theory and logic, where an intersection becomes the end. And as we said before, if I have 2 verifiable statements, I can make the finite conjunction, the finite end, which becomes the finite intersection in the topology. Or if I have verifiable statement, I can also test the OR, because as long as I have n statement, the one terminates successfully, I can say, the disjunction is true.
And you can test an infinite amount of ORs?
And that's the issue. How many ORs can I test? Because the thing is that I need to find one element of the OR, and then I can drop out. So if I have countably many ORs, I can go and find the one that terminates and stop. But if I have more than countably many, I'm not going to be able to do it. So the verifiable statements are closed under the countable OR, right? And now that you see, there is a little bit of a difference between the topology, because the topology tells you arbitrary OR, like arbitrary union. But then you think, okay, but I want my theory to be physically explorable with tests.
Yes.
And even if I give you an unlimited amount of time, the most that you're going to be able to do is test countably many.
Now, if you truly wanted it to be physical, wouldn't you say that it has to, you put some bound, like some Bekenstein bound or some informational bound, because we only have this universe, and so there'll be the heat death at some point, and so you put Graham's number as the ultimate large number?
Yeah, but remember, we're creating models. When we create physical theories, we create models that are valid under certain assumptions, right? So why are you going to worry about that when at the end of the day, I'm going to worry that I'm going to say that I have a system that is isolated?
So in other words, we currently think that the universe will end in a heat death. We don't know because that's already assuming some physical model. So let's just say finite and not think about all the interactions. And what I mean is that when people want to say some large number, they'll usually say that's 10 to the 600, and that's larger than the amount of atoms there are in the universe. They'll usually use the number of atoms. Well, maybe it should be the number of interactions between atoms, or which is a much larger number. But it doesn't matter. There exists some finite bound. I believe it could be Graham's number.
Yes.
You're saying even to calculate Graham's number as the largest finite bound, assume some other physical theory, and we're trying to not assume that, so we're just going to say finite, not a particular number that's finite.
No, I'm saying that I'm perfectly fine to assume that there are infinitely many things because it's in the model. And in the model, I can assume that there are infinitely many things. Even it's like the thermodynamic limit. You make the thermodynamic limit. You say you have infinitely many particles. What do you mean? I really mean a large amount of particles. But still in the math, you're going to do the limit with infinity. What is the problem? You do it. You know that you're making a model. So the model doesn't have to be factually correct. The model has to be a good approximation of what you do. Then in science, you also have another problem, is that you assume reproducibility. If you assume reproducibility, you're already saying, I can do it one more time.
Yeah.
And if you assume I can do it one more time, you're already getting infinity.
I see. Can we ever do something one more time, technically speaking?
Technically speaking, I know at some point I'm going to die, so no. But in the model, you assume that. You assume, well, okay, I'm not going to be able to do it somebody else. Like, really, we want to put the physical theory that, the sun is going to expand and destroy it's a model. So I don't see the problem of... So the problem is that, again, you need a justification to say that this model, like you need to know when the model holds. And so your model is, okay, I'm going to have an infinite amount of time. I will have all these tests. It's not even infinite, you see. It's arbitrarily large, which is not infinite. And if I have a procedure that has to cope for an arbitrarily large amount of time, because I can always do something one more time, you still need to give me an algorithm that have, countably many possible tests that it can run. Even if you're not going to run all of them, but the whole thing defined on arbitrary time is defined on countably many.
So at this point in your journey, it's 2010?
Oh, no, this I figured out in 2000, how was it? I don't know, 17.
Okay, so this is quite recent. Okay, that you were thinking about the...
So the whole thing worked like this. Up until 2012, which is when I moved to Michigan, I was sort of futzing around by myself, reading book, auditing classes on quantum field theory, reading book on quantum mechanics. I had absolutely no interest to do any of this. I was happy to do essentially engineering within a big computing. So I went at CERN, and then I remained in sort of big particle accelerator, and I was doing databases, wide area network, data distribution, security, cybersecurity. There's a lot of different things, control systems. I did a lot of these things. In 2012...
so it wasn't actually particle physics?
Well, I was in support of particle physics.
What I mean is, look, we can work on creating a TV show, or we could work on ensuring that the HDMI cables are plugged into the right place. They're both working on the TV show.
I'm working within the experiment, working on the software infrastructure that they have. Or I'm working at a facility that provides the acceleration, for example.